Cleared tissue light sheet microscope. We 3i have been in the business for a long time. We've been making microscopy systems since 1995, and we like to think of ourselves as having ownership of the commercial light sheet market. I mean, I know that there, of course, are other people out there. The Brooker guys, I think, are awesome. And so, you know, like Brooker, we have a very broad portfolio of light sheet microscopes. We started our journey into light sheet by manufacturing a commercial solution for lattice. And then we have something called Mariana's light sheet, which is a selective plane illumination microscope that's designed for smaller tissue, organoids, zebrafish, tissues, cells in culture. And then recently we developed our cleared tissue light sheet, which you can see here. One is because it's cool technology. It's something that's very different for us. I mean, a lot of the things that we have done, we 3i has focused on live cell imaging. So to take a product and introduce it into the community that's not a live cell imaging microscope was a little bit different for us. Paige told you a little bit about my background. Yeah, educated at Vandy, Nashville, Tennessee. Nashville, Tennessee, when I was there, was not as gentrified as it is now. I was there back in the mid 80s. Postdoc at Duke, and then after Duke, you know, I went out to University of Washington, and then I got attracted to a company that built at that time the first high-speed confocal. And so I've been working with laser microscopy systems for a long time, and working with confocal and then jumping to light sheet has just been a joy. I know that you guys have this journey. You're going to be looking at a lot of systems, but big thumbs up. Really love light sheet, and I hope that you guys decide to get our light sheet. But if not, whatever light sheet you get, because there's a lot of good products out there, I'm sure that you're going to enjoy it. And cleared tissue is also just amazing. So I'm going to start where most people, start with. Well, that's no good. Let me see. Why did that do that? We're going to start at the beginning, which will be, let's move this out of the way, which should be over here.
Yeah, we can listen for a minute.
Oh boy. Okay, sorry. We're going to go back through my deck. Sorry, guys. Oh, there we go. Okay, so we're going to start here. For those of you who may not be familiar, selective plane illumination microscopy, when you hear that phrase, mouthful, that means light sheet. This is a schematic, and I think that this was done by our friends at Zeiss, that just gives you the fundamentals. There is an excitation source. This excitation source is typically a coherent beam, a laser. And that laser is going to be converted into a sheet of light. And we'll talk about how that is done. It's two ways. One's static and one is dynamic. We use a dynamic light sheet. And then that sheet of light is going to interrogate selectively a plane through the sample. Sample is going to be fluorescent. So the fluorescent signal would be collected by some kind of detection optic and then shuttled off to a detector, a CMOS. We like using a back-thinned CMOS for a variety of reasons. But every instrument that you will see is going to have these fundamental features: laser, being converted, a coherent beam being converted into a light sheet, projecting selectively through a plane of the sample, exciting fluorescent probes. Those probes are going to be collected by a detection objective and then imaged with a CMOS or some kind of device. But at the core, and what I want to do for everyone I talk to is I want to give you information that will arm you to make intelligent decisions. At the core, a light sheet is a Gaussian beam. Ta-da! This is a Gaussian beam. This Gaussian beam was shot with my microscope, and scale bar down here, so 500 microns, I don't know, about 2 millimeters long. The things that I want you to know about this Gaussian beam, because you're going to hear this a lot, is this variable. So this variable defines the waist of a beam. Everybody's going to talk about their beam wastes. I think that's crap, but that's fine, because you need to have something, right? So the beam waist, this value is going to define the focal point, the narrowest portion of that Gaussian beam, because as that Gaussian beam projects across space, right, it's going to diffract. You can see, these elements here. Our beam is broadening. But the important part of the Gaussian beam, yeah, sure, the waist is important, but what's of real value is its Rayleigh length, and the Rayleigh length is shown here with these variables. I'm a Vanderbilt guy, so I've got to throw some equations into a talk. I think it was compulsory when I graduated. But in any case, this Rayleigh length is defined as the point where the waist has doubled in width. So why is this important? Because when we talk about the beam and when we talk about the light sheet that it creates, the part of the beam that's used to image is its confocal parameter. And the confocal parameter is 2 times its Rayleigh length. So let's just say that your imaging goon, not Paige, but me type of commercial imaging goon, says to you, I have a beam waist, and the narrowest beam waist that I can provide is 3 microns. Okay, la-di-da. What that person should be telling you is that my confocal parameter, what I'm imaging with, is probably about 6 microns. So very good thing to know, just something that you can interpret. So when people are talking to you, when other commercial people are speaking to you about their light sheet, one of the things they're going to pop out with is, this is my beam waist. So just in your mind, double it, because that's what they're going to be using when they actually image. So not so much this part, what we kind of see in red, but extending all the way out to this yellow part. That's what's going to be used to image your sample using a light sheet, confocal parameter. So how do you make a light sheet? I love this part. Pre-COVID, we used to do a lot of courses, and the whole light sheet thing was kind of mysterious to people. There's 2 ways to do it. One way to do it, if you have a 50 cc test tube at home or in the lab, just fill it with water and take a laser, and then this test tube, once it's filled with water, becomes a cylindrical lens. And what you'll see is that the beam no longer is a beam, but after it goes through the lens, it becomes a sheet of light. That's one way to do it, and that's called a static light sheet. Something you can ask the other commercial guys to use a static light sheet or dynamic light sheet. We use a dynamic light sheet. So what you're seeing right now is my chamber filled with a solution that has some fluorescence in it, fluorescein in it. We're going to stop it here just for a minute. So what you see is my chamber. You're going to see two excitation objectives, and that chamber filled with fluorescein water. You'll be able to see that beam, and you'll be able to see the nice little Gaussian beam. And then we're going to turn on a galvo, and that galvo is going to swing this beam, nice Gaussian beam. It's going to swing it back and forth really, really fast. And that's what's going to create the light sheet. Real cool thing to show, especially when people don't know what a light sheet is. But in our case, we create this light sheet dynamically. We create the light sheet dynamically for a couple of reasons, which we'll get into later. But one of the things that again you should know about a dynamic galvo-based versus a cylindrical lens static light sheet is that the static light sheets require less laser power. So, you know, there's this other thing that people will always look at. It's like, well, what's your laser power? What's your laser power? You know, if it's a dynamic system, you know, like the 3i one, or, you know, certainly the Zeiss one, since we pay a license fee to them, you know, the laser powers will be a lot more distractingly, but it's because they're using a dynamic light sheet rather than a static light sheet. Okay, so we know how to make a light sheet. So the next thing is, so the next thing is with this light sheet, in our case, we will, or in the sense of clear tissue, whether it's from me or the Brooker guys or Miltenny or the Zeiss folks, we're going to be imaging an organ. And it's a large organ, centimeters, not millimeters in size. And here, I'm just going to give you an example of a mouse brain, just so we can have a landmark, a milestone that we can stick a flag in. So in this case, this mouse brain is about 9 millimeters from cortical hemisphere to cortical hemisphere. And then from the olfactory bulb to its cerebellum, about 12 millimeters. And then from the top of the hemisphere down to about the hypothalamus, about 8 millimeters. So pretty large object, right? And then how are we going to interrogate that object? Well, we're going to use said light sheet. In this case, this light sheet, here's the scale bar, again, imaged with my rig. So this particular light sheet is going to be about 8.5 millimeters wide. That means I can interrogate said mouse brain with that light sheet, right? Problem. The problem is that all of the energy, remember our confocal parameter, all of the energy is going to be focused right there. So all of this stuff, like 90% of the light sheet is not going to have a whole lot of power. And so this becomes a problem when you're imaging something that large with a sheet or with an object that's large, and then extending your Gaussian beam so it's like whatever, 8-9 millimeters long. Problem is that when you look at the, in this case, this is a portion, a section about 1 millimeter thick, Thai-1 GFP mouse brain. And then, and what I've done is, here is our scale bar. So here is the Gaussian beam that I'm using, and single objective. And what you'll see is objective excitation is coming from the left side, so this side. So you can see that on this portion of the brain, the left side closest to our excitation objective, getting a lot of good information, right? This is pseudo color palette. So red is going to be bright, blue is going to be dim. And you would suspect that because this is my confocal parameter, the middle portion of the brain should be the brightest, but we're getting some scattering, right? And so not only do we have this beam that's very weak, that's also being scattered as we go across the brain. So from this left hemisphere to the right hemisphere, you see we've lost so many photons, right? We can see cortical pyramidal cells right over here in red that, you know, we see kind of in green over there. So we have this problem. We can create a beam that's that long. We can create a sheet from that beam that will interrogate this entire object from hemisphere to hemisphere, but it doesn't do it efficiently. So what we do with our microscope, and you know what, we're not unique about this, we're unique in the way that we do this, is we're going to take that confocal parameter and we're going to translate it using a spatial light modulator over a field of view. And in this case, the field of view is going to be about 2 millimeters. So now imagine I'm translating that confocal parameter across this field of view. And now I'm going to trigger, I'm going to harmonize with the camera when I'm capturing an image. So I'm just going to tell the camera to capture an image at the point where the confocal parameter is located. Now, of course, this happens very quickly, right? And you as a user are going to be blind to it, but it's just something that you should know. We all do it. We all do it differently. The Miltenyi guys do it mechanically. Not sure how the Zeiss guys do it. Who are those guys, Jessica? Oh, the live canvas guys, they buy the license, you know, to do this tiling. So we all do it. We just do it differently. And the difference will cause you, you know, either time or, you know, some other features, two, three, or four features that we'll talk about shortly. But anyway, that is the key to us. We're translating the confocal parameter across a field of view. So as a consequence, now we can get, you know, a nice uniform image of the brain. It looks like on this rig, the right side beam was a little bit brighter than the left beam. I don't know, maybe a little bit more power, maybe my alignment was better on the right side. But the point is, by taking that confocal parameter and translating it across 8 millimeters, we'll be able to provide you with you know, a more uniform looking organ. Okay, so why? So that's the why. And like I said, we're not unique to this. Everybody's going to do it. People are doing it a different way. One of the reasons why we do it this way, using a spatial light modulator to digitally modify the sheet, then translate the confocal parameter over the field of view, is that we're going to improve your optical sectioning and we're going to improve your axial resolution. Watch this. So, so what we're going to see here is, again, I'm just going to pound this into you guys. we're taking that beam, we're translating across the field of view. We're just going to capture the images that are aligned with the confocal parameter. We're going to do this region by region, usually 2 to 4 millimeter fields of view, and then we're going to do it into a Z plane so that we can provide you with this wonderful 3D image of a cleared organ. Now, one of the things, and I want to pause this video so that I can make a point. This is the VTN, ventral tegmental nuclear group, in a mouse. And this data set, this 3D volume that you're seeing, was captured using just a conventional beam. That beam is going to have a beam waist of about 20 microns. So that means my sheet is like frickin' 40, sorry, Paige, I didn't say frickin'. It's going to be really thick, right? 20 micron beam waist means my sheet is going to be about 40 microns. So as we look at this VTN, this group, look at these cells right here, or look at these cells right here. See how they stretch? That's a compromise in axial resolution. And then what I just did there was I changed the beam. Now the beam is being translated across the field of view. And if you look now at the VTN, look how pretty these cells are. They're nice and round. We now see the axons. This beam now becomes a 1 micron beam waist or a 3 micron sheet. And it provides me with better optical sectioning. It's providing me with better signal to noise, but it's also providing me with better axial resolution. And now when you can compare these two data sets, you can see, what happens with like a 40 micron sheet versus a 3 micron sheet. So why is that important? Well, it's important because of this. It's important because of this. Let's just say that you are interested in interrogating an organ. Interrogating it in this case means that I'm going to segment on these cell bodies in the hippocampus of this mouse. And my segmenting, I'm just going to do a small region. And then I'm going to take the parameters that were used to segment in this small region and then spread it over the entire organ, just because if I tried to segment on the whole thing, it would take a really long time. But by segmenting, I have the confidence, knowing that my axial resolution is great and knowing that I have good signal to noise, I can identify pretty quickly a small cluster of cells, program in a segmentation algorithm, and then bomb it throughout the entire hippocampus. And now I can do cell counts. And then I can do cell counts based upon, I don't know, cell size, for example, or maybe location, CA1 versus CA3, blah, blah, blah. Or what happens if I want to do something a little crazier? Purkinje cells, cerebellum, mouse. And in this case, what we were asked to do was just identify the primary and secondary dendrites of the Purkinje cell fan. In this case, what we were asked to do was something also a little bit more sophisticated. We were asked to segment on the vasculature in the brain. And again, you can do that, and it can be really time consuming, but it's much easier if you have the high signal to noise. And then you also have confidence that your axial resolution is good. That way you're not looking at, if you're looking at two vessels and they become one because of poor axial resolution, then you get bad data. So the key for us is that by providing you with good axial resolution and good signal to noise, by providing you with this very, very narrow beam, that we are providing you with the confidence that you'll be able to do your quantitative assessments with confidence. Okay, spatial light modulator. We've been talking about this. What is it? It's this thing right there. You're looking at the inside of my microscope. Laser is going to be coming from this direction. This is just a lens here. It's going to bounce off this mirror, and then it's going to go through a polarizing beam splitter. This again is the SLM. This is what we're going to program. After I've programmed something, a pattern, into the SLM, back through the polarizing beam splitter, off to a mirror. I don't know if you can see this very well, but this is the galvo, and the galvo is what's going to make, our light sheet. So what happens on the SLM? What happens on the SLM is that we are going to create patterns, and these patterns are going to do these crazy things to this beam, and does it very quickly, right? In this video, I just show how the patterns can change the angle of the beam, the position of the beam. I can do all kinds of crazy things with the spatial light modulator just by introducing a pattern. So this is an example of a pattern. Don't stare at this too long because it'll give you a headache. but I just want to give you an idea of what these patterns are. A pattern is a bitmap. It's composed of an aperture, the round thing, and that aperture is going to define the thickness of your beam. It also is composed of a grating, these black lines. And these black lines, the grating is going to define where the beam is in Z space. And then we are also going to have a lens effect. And that lens effect is going to define where the confocal parameter is being translated across the field of view. So three things. The pattern is going to be composed of an aperture, the grating, and then the lens to define where it is in space, in Z. This is important because we're going to have beams that have different wavelengths. And we know from whatever, first grade, that when we project light through a media, right, those beams are going to translate, they're going to refract at different angles. So what does that look like? Well, it looks like this. So what you see down here is our pattern that we've programmed into the SLM. And as that pattern is being translated, you see what it does to the beam. We've created this little confocal parameter, and then we're going to translate it across the field of view. Easy peasy. That's what we do. We're proud of it. We think it's cool. It may just be something you want to ask people about, you know, when you're seeing their light sheets, because, you know, again, it's going to be important. I can create any pattern that I want. In this case, this pattern will create 3 different beams. I can do it, right? I can create a Bessel beam, not very efficient for interrogating large objects, but again, I can do it. One of the things that we have done is we've created this very novel pattern. And this pattern creates a beam that is what we call a multiplex, a whole lot of beams. And these whole lot of beams do something that's very, very important, we feel, and that is it neutralizes shadows, striping artifacts. And this just came out this month from Silvestri Lab. But I wanted to point this out because it's a review. You know, you hear about striping, you hear about shadowing, you go like, oh yeah, this guy's microscope is crap because it had shadowing, or this guy's microscope is crap because it was shadowing or striping. This is emblematic. Every light sheet microscope is vulnerable to shadowing. This is going to be due to a variety of things. Maybe it's port clearing, maybe it's some objects floating in your index matching media, but all microscopes are vulnerable to this problem of shadowing or striping. So what I'm showing here are 2 images of the same plane of a hippocampus. And what I want to focus on are these, whatever is this pyramidal cell here. So on one hand, we've used this conventional beam, and then, you know, this is the image that we're getting of this hippocampus using a fusion BT back thinned SCMOS at 52 milliseconds using this beam waste, using this beam. Using this same beam waste, but introducing this pattern, which we call infinity. Now, this is the image I get. And I hope that you can agree with me on a couple of things. First one is I'm getting better signal to noise. It may be difficult for you to see here, but I have neutralized the striping. But the other thing is, in fact, let's go back one slide. If you look at this cell here, that's this cell here, and this cell now shows a saturation indicator, you know, this red mark. And so in addition to neutralizing my shadowing, and same Gaussian beam, The only difference is the pattern. Same exposure time. I've increased my signal to noise, so much so at 52 milliseconds, I'm now getting a saturation warning in my image. And as you can see, when we look at our data, right, this is min and max count. I have gone from at 52 milliseconds using a conventional beam, a max count of, let's say 2,600 gray values. And then of course, with the saturation warning, I'm pinging the camera. Okay, so infinity beam. Here is what infinity beam does. This is why we think it's so cool. Same thing, hippocampus of a mouse, Thigh1 GFP, and you can see these stripes here. Big stripe there, bunch of little stripes, and this isn't camera noise. These are striping artifacts that may come from, I don't know, me, Jessica. I think it's Pia. I think there's something very peculiar about the meninges, and there's just something about those epithelial cells that will cause the striping. And you can see there's a lot of meninges down here, and also blood vessels. And you can see there's a lot of striping over here, and that becomes neutralized when we deploy this infinity beam. How does this work? Here's where you get to take a look at our microscope. This is a live image. You're seeing our interface right here, very, very clean. I'm going through and I'm just focusing a little bit so that you can see that this is a live image. What I did in this particular experiment was I put down an indicator, a region of interest. The thing is 1, and then we can show a number of statistics here. In this case, the mean gray value within that region is about 700 counts. So what I'm going to do now is I'm going to put in this new pattern into the spatial light modulator, and you guys wouldn't have to do this as investigators. This is something that we set up for you. Just want to show you how quickly this is done. So we load this pattern, we press the magical button, and then a repertoire of patterns are going to be generated and placed into the SLM. And now when I go back live, look on the left, I'm going to get enhanced signal to noise, bam, and I'm going to lose that striping artifact. It happens very, very quickly. It's a really cool feature. We're very, very proud of that feature. And if we go back and look at our region of interest, now we see instead of 700 counts, we're at 2,400 counts. So we've clearly increased our signal to noise. And then now in this experiment, what I want to do is go back and load the regular pattern. And so you'll see what that pattern looks like. There's our aperture, there's our gratings. And then we're not going to put any lens effect here. So it'll just be a straight out beam. We're going to load that pattern into the spatial light modulator. Takes about 15 seconds, I think 10 seconds to completely load the repertoire. And then we'll go back and click on live, and oh, we got the old image. Our signal to noise has decreased, and notice, right? I didn't make any change on my exposure time. No change to the exposure time. Camera's still doing what it's doing. And now what I want to do is I'm going to go back to an area of the brain where I know I'm going to see a lot of striping, and it's right down there, between the hippocampus and the midbrain. See a lot of striping, all these stripes right here, right? That's a crazy, crazy amount of striping. And then I'm going to go back, and then I'm going to reload that infinity pattern. And again, these are things that you guys have to do. I'm just showing you what this is. So it's also Paige, it's this great teaching tool. I mean, if you want to teach people about light sheet microscopy, this is it's a really, really fun microscope. In any case, so we've loaded the patterns. I think I'm talking too fast. People that have dialed in, sorry. And then we go back, we're going to neutralize those patterns. Bam. Awesome. It's crazy. It's just, I love spatial light modulators. They're just so cool. So let's move on. So we've talked about neutralizing noise. striping. The other thing that people come to us all the time with, they always want to do multi-channel imaging. Multi-channel imaging is kind of a pain in the butt. In this case, this is a sample from our friends at the University of Miami. 3 different epithelial cells in the brain of a mouse. Beautiful, beautiful sample. And then this is a spinal cord from a separate mouse. This one I kind of hated when I was imaging it, but it was really cool after the fact, you know, when I could see that we didn't have any problems with chromatic aberration. I mean, all of the different colors lined up very nicely. And so chromatic correction, what's the problem? Well, as I was saying earlier, right? We have media. Our critter, our sample is sitting in a bath of index matching solution. And so the rays of light, and you know, we're just showing one example here, the rays of light are going to bend at different angles depending upon their wavelength. But it's a little bit more complex. What I'm showing here are 1, 2, 3, 4 different beams in the media from a 405 laser, DAPI, from a 488 laser, GFP, 561 laser, which we'd use to do like, I don't know, Texas Red, M Cherry, TD Tomato, and then a 640 beam. We can also do a 785 beam. But if you look, you'll see that our confocal parameters shifted a bit, right? So here in the 405 beam, it shifted. The 488 is actually the one I was focusing on. We have a little bit of shift at the 561 laser, huge, huge shift on the 640 beam. So we have 2 problems here. The problem is axial and lateral chromatic aberration correction. And of course, we use our friendly spatial light modulator to address this. What you're seeing here is just a shot from the user interface where we have, in this case, there was 5 lasers, but I don't think that we were shooting with the 785 in this experiment. But you see that the pattern, the grading, and that grading is going to define where that beam is in space, right? In Z space. The grading is going to differ for the 4, 5 different lasers. And then our aperture is also going to have to differ because of again, refraction of the beam. And then, we're also going to have some Z offsets to ensure that those beams, those light sheets, are interrogating the same place, the same plane in the organ. And so what does that look like? Well, here. So what I'm doing is I'm just moving up and down, corrected and uncorrected. And as you can see, when we don't correct with the spatial light modulator, you can see how the blood vessels, they're not lining up correctly because of either lateral or axial chromatic aberration. So we do this on the fly. We do it a priori while we're shooting, because doing it the alternative way, shooting the organ 3 times, 4 times, and then trying to line up terabytes of data, trust me, can be quite onerous. I'm nearly out of time here. So let's see what we've learned today. Lesson 1. CTLS, our cleared tissue light sheet microscope, is a selective plane illumination microscope. It's a light sheet microscope, right? 2, big thing, it uses a spatial light modulator to digitally shape the light sheet. And so by doing that, we can provide you with a lot of stuff, but primarily good axial resolution, good optical sectioning. Secondly, we can make all kind of crazy patterns, but the craziest pattern we make is this pattern that creates infinity beam, which neutralizes the strafing. And then we have a means to a priori, while we're shooting in advance, neutralize the aberrations that are caused by lateral and chromatic, lateral and axial chromatic aberration from the different wavelengths of the beam. CTLS, designed to image large cleared organs, right? Centimeters. We can do millimeters. you'll see an organ in a minute that was pretty small, but we like doing big objects. I know that, in my last few minutes, talked a lot about neural stuff, right? The brain is just a joy. For me, it's just one of the most beautiful organs to image. And they're just so much fun because they're so pretty, whether it's vasculature of the brain, whether it's a Thigh-1 GFP or whatever mouse, where we can look at neurons and their tracks, and then even interrogate the individual cell bodies. And then, I don't know, if you want to get nutty, try to interrogate its axons. But we've done this whole portfolio. This is an intestine from a group that we're working with at Albert Einstein in the Bronx in New York. So, this is the hind paw. Hind paw? It's the paw of a mouse. In this case, the bone was cleared. This is from a group, a nephrology group at University of Texas Southwest in Dallas, where they were interested in, counting is it nephrons, glomeruli, something. In any case, we have this full portfolio where we've imaged a lot more than just brain. This is this is crazy. This is the jawbone of a mouse. The pockets that you see are where the teeth are, and they've been cleared, right? So what we're looking at here is just the innervation, the vascular innervation around the jawbone, the teeth of the mouse. This is a mammary gland. We're working with a few investigators who are very interested in looking at the metastases of cancers in different organs. Mammary gland, of course, as you can imagine, would be a very popular organ to interrogate. And then, this is the one I was talking about. This is a really small organ. This is the cochlea of a mouse. So this is a cochlea of a mouse, and what we did was we just painted the neural portions, but this is also showing vasculature. Another shot of the kidney, but my point is, mouse cochlea is tiny, and we're able to image it. And the one thing I didn't talk about is we can also image a whole mouse. We're working with Ali's group and Ali Ertrich's group at Helmholtz. This mouse actually comes from a development partner at Beijing Institute of Brain Research. But my point is that we can do this whole portfolio of tissue clearing. And I think I'm almost out of time. So yeah, man, CTLS rocks. You guys are going to have fun. We're going to have fun when I come out and demo for you. My name again, in case you want to tell my boss I suck. Ed Lachica. I'm with Intelligent Imaging, serving the planet since 1995. I'll see you guys soon.